Most routing decisions are based only on destination IP address. But what if that's not enough? What if you want different devices or different traffic to take different paths even if they're heading to the same place? That's where policy-based routing or PBR comes in. And in this video, I'll show you how to use it to control traffic paths with Cisco CLI. Let me take you through a real-world scenario. It's 3 a.m. and your backup server is doing exactly what it's supposed to do, uploading data off-site, syncing with cloud storage in AWS or some other remote location. The problem with this, it's using the same internet link your production traffic relies on during the day. What started as a good idea, automating your backups, is now flooding your production WAN link. If those backups overrun into business hours, users are hit with slow applications and login delays. Even worse, your monitoring systems might start seeing packet loss or high latency, triggering false alerts. Next thing you know, an on-call engineer is getting woken at 3 a.m. to investigate a down router that's perfectly fine. In enterprise networks, there's typically more than one internet connection available. Maybe a backup ISP line that's just sitting idle most of the time. Why not use that backup link for the remote backups or heavy batch jobs? In this lab, we'll simulate exactly that setup using Cisco CLI and policy-based routing. Let's take a look at the topology. We've got a collapsed core layer 3 switch, which handles all the internal routing. There's two VLANs, one for the app server and one for the backup server, each on their own subnet. The core switch connects to two separate WAN routers, a primary WAN router for production traffic and a secondary WAN router that we will be routing traffic sourced from the backup server through. Both WAN routers lead to a simulated cloud destination. We'll call it AWS storage with a loopback address of 9.9.9.9. That's where the backup traffic is headed. Our goal is simple. Make sure that the backup server sends its traffic to 9.9.9.9 over the backup WAN link, while the app server and everything else continues to use the production link. First of all, let's verify that all the traffic is routing via that production link from both the application server and the backup server. Just a quick note here. This is a lab environment, so I'm not doing any natting here. But in a real-world setup, your backup server would be natted to a public IP address, which would be configured either on the WAN router or a perimeter firewall. That's how traffic from somewhere like AWS would know how to route the return traffic. So just from the application server, we're just going to do a quick trace to 9.9.9.9, which is that loopback interface we have configured on the AWS storage router. So as you can see, the first hop here is 172.16.10.1, which is the VLAN 10 interface on the core switch. The next hop, however, is traversing the point-to-point link to the ISP production router. So we'll just jump over onto the backup server and do the same. We'll just do a trace to 9.9.9.9. So we can see the first hop is the VLAN 30 interface on the core switch. And also you can see the second hop here from the core switch is traversing that point-to-point link to the ISP production router. And this is the issue that we are faced with. So the traffic from the application server and the backup server are taking the same path, the same link. If we start firing large backups over that link, our production applications are going to feel it. Right now, both servers are using the default route and there's no logic to treat backup traffic any differently. So let's fix that. We'll start by creating an access list on the core switch to match the traffic that we care about. In this case, it's traffic from the backup server to the AWS backup target. We'll define an extended access list that catches exactly that traffic. So just from core switch here, the commands are IP access list extended, and we'll call this backup to AWS. We then want to match the traffic. So that's permit IP host, because it's a single IP address, 172.16.30.130, that's the IP address of the backup server, and the destination host, another single IP address, 9.9.9.9, which is the AWS storage. It's worth noting in this example I'm matching on source and destination IP address only, but just so you know, extended access lists can match on much more than that. You can match specific ports, protocols like UDP or TCP, or even things like ICMP types. So if you wanted to route only FTP backups differently or isolate voice over IP traffic, for example, you could absolutely do that. PBR is very flexible. So, now that we've matched the traffic, the next step is to create a route map. This is where the decision happens. We say, if the traffic matches our ACL, push it to the backup link instead of using the default route. Here are the commands to create that route map. So we have route map, and then we will name the route map, PBR underscore backups. Permit, which means if traffic matches the condition below, apply the policy. And then we have sequence number 10. It lets you have multiple entries if needed. Match other traffic in the future. Press enter. The next step is to match the access list that we created previously to this route map. The command is match IP address and then the name of the extended access list that we created. Press enter on that. So we've now created the route map. We have told the route map to look at the traffic that we have specified in the access list, which is the source IP address of the backup server and the destination IP address of the AWS storage. The last step here is to set the next hop to the backup router. The command for this, set IP next hop 10.0.30.1, which is the LAN facing interface of the backup router. The final configuration step here is to apply the route map to the VLAN interface where the backup traffic is being routed. In our case, it's VLAN 30. This ensures that the traffic from the backup server is evaluated against our policy before it even looks at the routing table. And since we know that there will be a match based on our ACL, the traffic will then be routed to the backup WAN link. So, to make this final configuration, we'll go into interface VLAN 30 and the command is simply IP policy, route map, and the name of the route map that we created. But before I implement this, I'm just going to do a trace from the backup server first, just to confirm that it is traversing the production link. So as you can see from the trace, it is traversing the production router. Let's go back to the core switch here and implement that configuration. And we'll just go back and do that same trace. And as you can see there, it is now traversing the backup link 10.0.30.1. And we will also just do a trace from the app server just to confirm the app server is still using the production link as we would expect it to. And there you go. So that's 10.0.10.1, which is the LAN facing interface of the production ISP link. So there you have it, folks. With just a few CLI commands, we're using policy-based routing to take control of the backup traffic and send it over a dedicated link. The rest of the network stays untouched, the default route remains clean, and we've alleviated congestion on that production WAN link. This is a great example of how a small change at the edge can make a big difference to performance. If this helped you out, folks, or sparked an idea in your own network, please subscribe, like my videos, and let me know in the comments. And as always, no fluff, just real world networking. I'll see you in the next one.